Well, hello again all. We are days away from writing our paper 1 CAPS Physics Matric Paper, and we're going to go and look at the question 3 of the paper, which is your vertical projectile motion. We're going to look at 2020 right up to 2017 papers. Okay, and then we're just not teaching this, but we're just making sure that you know how to do the problem. So I am going to present my entire screen, and let's have a look at those papers. So let's go to question 3 of 2020. So we have a small ball is dropped from a height of 2 meters. There's a graph, position versus time. Bounces a few times after landing on a cement floor. Ignore air friction. The position time graph below, not drawn to scale, represents the motion of the ball. Now, what's nice about position time graphs? They actually look like the actual motion of the ball. So there you see a ball bouncing and bouncing. Notice each bounce gets lower in height. It doesn't bounce as high unless you've got some miracle substance that doesn't lose any energy. And then what do these little gaps represent? Those are the gaps in time as the ball is, where's this? This must be the ground, right? It's hit the ground and the ball's being squashed and then it jumps back up. Then it's squashed again, jumps back up. So here's where it hits the ground the first time. There's the maximum height after the bounce. Hits the ground a second time. There's the maximum height. So it's dropped from 2, bounces to 1.85, bounces to 1.2. And here's the time intervals that it takes. Everyone understand the problem? I love graphs. They're just a story. Daddy, please tell me a story. That's the way I tell myself not to be scared of graphs anymore, because they're just telling a story. Okay. Now, in vertical projectile motion, which is your question 3, is this a vector problem? Yes, you're going to go, this is a vector problem. In this case, things are starting falling down. So normally you choose your starting direction, which is down. In this case, would be negative. I would be positive. So in this case, you could choose downwards is positive, or you could choose upwards is positive. What I think they've done here is they've got this 2, that's a positive direction, positive 2, and then it falls downwards to 0. So I'm going to choose positive is upwards. Okay, define the term free fall. So you've got to choose a direction. Find the term free fall. In all question 3s, they're going to ask you, what is a projectile, or define free fall. It's the same thing. It's where there's one force, and that is the force of gravity acting on the object in the air. Okay, there's no friction, no air friction. It is just the force of gravity acting in the air. The other way they're going to try and catch you is they're going to try and say, is the acceleration does the acceleration change if it's going up or down? No, the acceleration is always 9,8 and it's always down. So those are the 2 things. So how are you going to define it? And I would always go and look at the memo, look for the definitions, but it's an object in the air experiences just one force, and that is the force of gravity. Use the graph to determine the time that the ball is in contact with the floor before the first bounce. You see, this is bad English here. During the first bounce, not before the first bounce. Because the time that is in contact, unless they're calling this section, is the bounce back. But they're not including this. So it's bad English. Okay, so the time that it's in contact, well, there it hits the floor, there it leaves. In the interim, it's been squashed. What's 0.67 minus 0.64? It's 0.03, and that's going to be your answer. Is that easy enough? The time it takes the ball to reach its maximum height to the first bounce. So in the section question 3, you're always going to use your equations of motion, right? You've got them now on your data sheet. So you know the initial velocity, and I would choose up as positive. Your initial, so I would put, your distance or your displacement, delta y, is going to be that. The time is going to be 0.67. Now, what do you know about symmetry here? And 1,90. If you subtract that from that and divide it by 2, in the exact middle is going to be the time it takes to get to the top. So I know the time it takes to get to the top, and I know the height to the top. So to find the time it takes to reach the top, I would just subtract that from that and divide the difference by 2, and there would be the answer. It's only worth 2 marks. Or we could use an equation of motion. The speed at which the ball leaves the floor at the first bounce. Okay, if we know the time to the top, we know the final velocity at the top is 0, right? We know the time it took, we know the distance, so we can work out V initial. V initial, there's a formula that involves V final, time, and distance or displacement upwards, which is 1,85. And so you're going to use that. Very easy to calculate the speed. The time t indicated on the graph. Okay, so again here, you know that in the middle of the graph, it's going to take a certain length of time to get to the top. So using your equation of motion, you know that the distance that it goes is 1,2. So if you know the height that it goes, you're going to be able to work out the initial velocity if you note that the final velocity there is 0. So you work out the initial velocity, and then you're going to find the time it takes to get to the top, and then you're going to double it to get that time. So if you take 1,97, you work out the time to the top, 1,97 plus that time again, you're going to find t. I don't see anything difficult there. And so that was last year's paper. Looks pretty easy. Let's go to 2019. Okay. A stone is, so this is a vector problem. A stone is thrown upwards, positive. I always like positive upwards at V initial 10 meters per second. Is that a positive 10? Yes, it's a positive 10. What other values do we know? Must we start writing our variables down? Yes. We know that the gravity is going to be minus 9,8. So always get your positives and negatives. And it's from the edge of a building, which is 40 meters high. Now, always when you're thrown from a building and you've got the ground, you're gonna be working things from the top of the building, and they're going to ask a question: how high is it from the ground? Don't forget, you always got to add the height of the building to the height that things reach. Okay, define free fall again. You just did it in the last 2020, 2019, and there's only one force. That's the force of gravity acting on an object in the air. Calculate the maximum height above the ground in capitals the stone reaches. Well, look, you know G, which is minus 9,8. You know V initial. You know that at the top, where it reaches the top, its V final is 0. So you're just going to find an equation of motion, and you're going to work out the height that it reaches. And then to that, you're going to add your 40 to get the height above the ground, 4 marks. Write down the magnitude and direction of the acceleration of the stone at the maximum height. You see, they always try and catch you with this question if you've been through this a few times. Acceleration of any object in free fall, whether it's going up, down, or just reach the top, is always minus 9,8. The acceleration doesn't change. So the magnitude is 9,8. The direction is down. Stone B is dropped from rest from the edge of the roof X seconds after A. So A is thrown up, and then X seconds later, B is dropped from rest, meaning it's not thrown, it's just let go. Stone A passes stone B when the two stones are 29,74 meters above the ground. Calculate the value of X, or the time. So here would be where they pass, which is 29 meters above the ground. So to be about there. Okay, so what do we know in this kind of problem? How are you going to solve this kind of problem? And stone B is dropped from it. Calculate the value of the time. Okay, so what are you going to do? What do we know about the point where they pass? We know they're at the same position at the same time. So we're going to work out probably simultaneous equations for stone A and stone B, where they both at the same distance that they've been dropped from the top. So the first thing I would do is I would subtract 29,74 from 40 to get the actual height above the ground, the distance that each stone A and stone B fall. Okay, because your equations of motion don't care about the ground. They all work from where you start to where you end. Okay, so this, don't forget, this is below where you start, so that position is positive or negative? Negative. If you make it positive, you are screwed. Okay, so delta y is going to be minus, what's 40 minus 29,74? It's going to be 10.26 meters. So it's minus 10.26 is going to be the distance that each of them fall. So if you drop stone B, how long does it take to drop a distance of 10.26 meters? Well, it's easy peasy to work it out, right? Your equations of motion. So let's presume you know you can work out the time for that. And then the same thing, you can take this stone thrown up, it reaches its top and it comes down. So it's delta y is also 10.26. So you work out the time taken for both stones to get to that same position, and then you subtract their 2 times. So you work out the time for stone A to end up to 10.26. You can just, one equation of motion. Stone B is dropped, so what's its initial velocity? 0. What's its final velocity? It's going to be something negative. Who cares? You just know that the distance is 10.26. You could always work out the time, therefore. So you've got the time for both, and you subtract the 2, and that is x. Looks easy enough. Let's have a look at 2018's paper. In a competition, participants must attempt to throw a ball vertically upwards past point T. So look, they also have a starting height above the ground of 1.6 meters. You always got to take into account that when you use your equations of motion, they're always measured from your starting position. Your starting position, not the ground. Point T is 3.7 meters above the ground. Point T may or may not be the highest point during the motion of the ball. One participant throws the ball vertically upwards at a velocity of 7.5 meters from a point that is 1.6 above the ground, as shown in the diagram. Ignore the effects of air resistance. Okay. In which direction is the net force acting on the ball while it moves towards point T? The net force, folks, is always downwards, and that's called its weight. Okay. It's downwards. In which direction is the net force? Downwards. Choose from upwards or downwards. Give a reason, because it experiences the force of weight, which is always down. Calculate the time taken by the ball to reach its maximum height. Okay, look, if you got an initial velocity. Now, I said this is a vector problem. Up is positive. Its starting velocity is going to be positive 7.5. Gravity is minus 9.8. And at the top, it is 0 meters per second is its V final. Okay, so you've got V initial, positive, V final, 0. And then you're just going to work out delta y. And then you're going to add delta y to 1.6, and you're going to see if it comes to less or more than 0.37. If it's less, it didn't reach the height. If it's more, it did reach the height. So once you've calculated the time, which is easy enough, you just use an equation. And then you work out the distance, which I've said. Draw a velocity time graph of the motion of the ball from the instant it is thrown upwards until it reaches its highest point. Calculate the following on the graph that indicate the initial velocity and the final velocity time taken to reach the highest point. So it's from the time it's released till it reaches its highest point. I think I'll stop sharing here and just draw that on the board. What are they asking here? Draw velocity time graph. Okay, just watch. When you draw velocity time graphs, the graph, if you've chosen downwards as negative and upwards as positive, right? You take your right hand and you move it like this, at diagonally down. And that is going to be what your velocity time graph looks like. It's always diagonally down. So what is your starting? So you're going to have velocity on the y-axis, you're going to have time on the x-axis, and your starting velocity of the ball is going to be what? Your 7.5 meters per second. And when it reaches its maximum point, which means where it hits the x-axis, is going to be 0, because it's stopped moving. So your velocity is going to be 0. So you've worked out the time that it took to do that. And so you're going to draw that on your graph. I just will stop sharing and just draw that graph quickly. So here's going to be your time in seconds, heading, velocity versus time graph. Naught, you're going to have velocity meters per second in brackets. You're going to have all the good stuff. And then you're going to have, it started at 7 point something and it got to there. It's straight line graph. This is going to be your 7 point whatever it was, starting velocity. Here's where it reaches its maximum height. You worked out the time, so you can fill that in, whatever it took. Was it 1 or 2 seconds to get there? You work that out in one of your answers. You're going to draw that, put that number there. You're going to put your starting velocity there. You're going to get your marks. Okay, easy peasy. So that 2018 looked pretty easy. Let's just have a look at 2017. 2017, stone A is projected vertically upwards at a speed of 12 meters per second from a height h above the ground. Ignore the effects of air resistance. Calculate the time taken for stone A to reach its maximum height. Now, come on. I don't know why people don't get full marks for these vertical projectile problems. Maybe there's something difficult here. So if you know its initial velocity, and is that a positive or negative? Yes, always choose. If it's a vector problem, upwards is positive because so upwards is positive. Gravity is minus 9,8. So you've got a starting initial velocity. You've got a final velocity when it reaches its maximum height is going to be 0. What's there to know? This is a gift of 3 marks. Calculate the time for stone A to reach its maximum height. Just use your equations of motion. Calculate the speed v with which B is thrown downwards. So it says when A reaches its maximum height, the speed of stone B is 3v. Now I know that most, let's just say, stone B is thrown vertically downwards from the same height at an unknown speed. So B is not just dropped from rest, as in it is thrown at a v. And then it reaches, and then it says when stone A reaches its maximum height, which we know the time taken to reach its maximum height. So that time, by that time, stone B's velocity is triple what it started. Calculate the speed v with which stone B is thrown downwards. Okay. So again, you're going to use an equation of motion. So now we know the time that it took A to reach the top. That's the same time it takes B to reach 3v. So what are you going to do? It's not hard to work with v and 3v. You're going to choose an equation of motion that involves initial velocity, final velocity, and time. And you're going to put for your initial velocity minus v because it's going down. Its final velocity minus 3v. Gravity minus 9,8, and you're going to work out v. So the v's you'll cancel out, and so you'll be able to calculate v. Doesn't look difficult. Calculate the height h. Okay. So it's thrown from a height which they don't give us. You see, this has become a mathematical problem. Let's just see how we're going to calculate h. Calculate the height h. Now, what do they tell us about h? Stone A is projected vertically upwards at a speed of 12 meters per second from a height h above the ground. We know how long it took to get how do we calculate h? Calculate the time for A to reach. We know its maximum height. We found that. When stone A reaches its maximum height, the speed of stone B is 3v. Right? That wasn't easy. That wasn't hard, I mean. Oh, here's the information we need to find h. Here. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate H. Okay, that's the missing piece of information. I was just wondering how we would calculate the height. Okay, so what are we told? At the instant stone A passes its initial position on its way down, stone B hits the ground. Okay, so we've already calculated the time that stone A takes to get to its maximum height. We double it, and that's the time it takes to get back to where it started, right? So we double the answer to 3.1. So now we know the time that stone A is taken to go up and come back to where B starts. Now, we've worked out the initial velocity of B, and we know that in the same length of time, which was double the answer of 3.1, stone B hits the ground. Okay, so now we're going to say that we've got a time, we've got an initial velocity, and what have we got enough to calculate the height? We've got initial velocity, which was V. We've got a time, yeah. If we've got an initial velocity, we've got G, V equals U plus AT. V final equals V initial plus acceleration times time, yeah. And so we can find, we start working out values, and it shouldn't be at all difficult. Therefore, we may have to find, first of all, the time, and then we will find the height. I think we've got to find the time first. We know the time. We know G. We might have to find the final velocity, and then we could calculate the height. So we may have to go through a step, but we've got everything we need to know to do it. Sketch a velocity time graph for the complete motions of stone A and B on the same set of axes. Label your graphs for stone A and B. Show the time taken for A to reach its maximum height, the velocity with which B is thrown downwards. Okay, let's just stop sharing there for a moment. Let me see if I can try and remember all this. And we'll stop presenting and then draw this on the board. Okay, so we've worked those all out. So we're going to have a velocity time graph. So velocity versus time graph, we're going to have stone A and stone B. And so stone A was thrown, it had a positive starting velocity. So this is going to be our time in seconds. This is going to be our velocity in meters per second. Don't forget to put meters per second in brackets. Don't forget naught. I think we're going to need a negative velocity as well. So our graph goes below. So stone A starts at its starting velocity, reaches the top. It then comes down to where it started. And at that, and what was stone B doing at, so there would be your graph. By the time, this is stone A. Starts there, reaches the top, comes back to its starting position. This, we would fill in the time that it took for stone A to reach the maximum height. Then it said that B was thrown down, I think at the same time, was it? Just let me check this out. I just want to check what the problem said. When stone A reaches, B is thrown vertically downwards from the same height at a constant speed. Okay, so so B was thrown down from the start at a certain velocity, a certain negative velocity, which we worked out what V was. And then the moment it was thrown down, it still continues, and this must carry on till, so there's minus V, or V. What's the starting velocity, which was a negative value of, this is stone V. it was thrown down at the same time that stone A was thrown. So if it's thrown down, its velocity is negative, and this must continue, and then B hits the ground just as A is reaching its same position. So this must be just a little bit longer there. And they asked us to show, what did they ask us to show? Just sorry, let me have another look again. The time taken for stone A to reach its maximum height, so we worked that out, so we fill in whatever value that is there. The velocity with which B is thrown downwards, okay, that was the V that we worked out, which is there. And then both these graphs must be parallel to each other. They're parallel to each other. It's been a while since I've done maths. Parallel to each other. Okay. And that slope of that graph is always 9,8. So that didn't look difficult at all. And I think that's it for 2017's paper. So we've done all 4 papers. Right. So I think I'm going to stop there with the Newton, with question number 3. We'll do this, I think, one at a time. So I'm going to just stop recording.